All right, everybody. I'm going to do this as quickly as I can because I swear to you, I could probably gush on for 3 hours about this stuff. So I'm going to try and move relatively quickly here. So yes, this is about special relativity developed by Albert Einstein, more or less, in the year 1905. That's going to show up time and time again. So yes, I'm including dates now, but because it's just going to be fascinating. To start off with this special relativity thing, I want to talk about what we call Galilean relativity. So relativity is not anything new. That's something we've learned actually at the beginning of class. Remember relative motion? This is just going to be a quick review of relative motion. So here you are on the surface of the Earth, and you look up and you see my cat Bella flying through the sky, moving at 20 meters per second to the right. So here's the velocity of Bella with respect to the Earth is 20 meters per second. And here's the velocity of you with respect to the Earth. You're at rest. Both of you are in what we call an inertial reference frame. We talked about that as well. If you're moving at rest or at constant velocity. In other words, if you're not accelerating, you're at an inertial reference frame. However, Bella throws a pink sphere. So she throws a pink sphere, and it goes this way. Let's see, let's make it a little bit slower because it's going to be the speed of this sphere. You know what? Let's make it a little bit faster. Why the heck not? So it goes like that, and then the speed of this sphere, the velocity of this sphere, so the sphere with respect to Bella, is 30 meters per second. So she throws the sphere at 30 meters per second to the right. And so when she looks at it, she sees it as moving at 30 meters per second. However, you look at it, and you see, well, Bella is moving at 20 meters per second. She throws it at what she looks at as 30 meters per second. You go, oh, the velocity of the velocity of the sphere with respect to the Earth is going to be, so if we remember how to do this, it's the velocity of the sphere with respect to Bella plus the velocity of Bella with respect to the Earth. Remember, you can join those two things and you get the velocity of the sphere with respect to the Earth is going to be, well, it's going to be 20 plus 30. And so the velocity of the sphere with respect to the Earth, it's going to be 50 meters per second. Bam, nailed it. So you perceive the ball as going 50 meters per second. However, Bella sees it as going 30. And that was the idea of Galilean relativity, that depending on how things are moving, they'll perceive different things. You know, they'll look at the same object and say, oh, I see that as going different speeds. Okay, so we talked about you guys saw the video about Maxwell's equations. And that from Maxwell's equations, you end up getting this thing that the speed of light, we tend to say c is the speed of light, ended up from Maxwell's equations, the solution shows up time and time again that it's equal to 1 over the square root of epsilon naught times mu naught. And if you look up these constants, and I encourage you to look them up because it's a fun calculation, and plug those all in, you'll get that the speed of light is 3 times 10 to the 8 meters per second. And it shows up time and time again, constant. And physicists at this time went, you know what, Maxwell's equations is doing a great job expressing electricity and magnetism and electromagnetism and electromagnetic radiation, but something must be wrong with them because they keep saying that the speed of light is constant. That can't be true because, let's go back, because if Bella was instead shooting out a light beam, like a flashlight or something, like a bit of light, well, she would see it as going as, some speed. Maybe it's 3 times 10 to the 8 meters per second. However, I would see her, if you were down here, you would see Bella as going, oh, it's 3 times 10 to the 8 plus Bella's velocity. And that would be the total velocity. So that can't be true. Something must be wrong with Maxwell's equations, is what other physicists said. Which, by the way, I got to mention as well, some of my favorites. So this was kind of like nearing the end of the 1800s, and many physicists were basically going, well, we almost got this physics thing wrapped up. We got all the kind of the general ideas wrapped up, and once we get them figured out, really the rest of physics is just going to be nitpicking. It's just going to be puzzle solving and getting things back to, figuring out the specifics. We'll have a general equation that expresses everything about the universe. We can express the universe in terms of particles and waves, and then we'll have this sort of general equation that expresses everything, and everything else will be just little details. Then 1905, and Albert Einstein decides, you know what? I got other ideas for you. So Albert Einstein looked at Maxwell's equations, and he said, you know what? Let's go back there really quickly. He said, you know what? I don't know. I'm looking at, I dig Maxwell's equations. I'm happy with what they're doing. I think we're all wrong. I think the speed of light is always 3 times 10 to the 8 meters per second. So what if the speed of light, c, is always constant in a vacuum? What would that mean? What would happen? That's kind of what he started off with. He said, okay, what if, all of Maxwell's equations are explaining to us really the theory, is really explaining to us reality, and the speed of light is a constant. What would that mean? What would have to change? How does physics change as a result of this? Well, he went into it. And he boiled these things down into 2 postulates. And the first postulate is that the laws of physics are the same in all inertial reference frames. No matter where you are in the universe, he says, and no matter what perspective you are coming from, if you are in an inertial reference frame, which is similar to what Newton did, right? If you are in an inertial reference frame, the laws of physics are the same. What's a law of physics? Here's a law of physics. F net equals ma. That's a law of physics. Any physicist would agree with that. There you go. I'm not going to get too big. Another law of physics. Momentum in any system that does not experience a net force or a net impulse is going to be conserved. Another law of physics. Energy where no work is done is going to be conserved. All these things are laws of physics. And so what Einstein's saying is that if you're in an inertial frame, all the laws of physics are going to be the same. Momentum is going to be conserved, F net equals ma, blah, blah, blah. No matter what experiment you can do. And he even kind of took this a little bit further. He said, if you're in like a closed space, if you're standing there and you're in an enclosed space that's not accelerating, there's no way you can tell if you're accelerating or moving at a constant speed. You could be moving at a constant speed, or you could be at rest. You don't know. If you're not accelerating, you have no idea, and you can, no matter what experiment you can do F net equals ma experiments, you can do this, you can do any experiment, you would have no idea. You could not tell. So that's kind of, and that is built upon with general relativity, and we'll get to that a little bit later. So now we're going to move on to what about the second postulate, which is the one that I kind of just mentioned, which is that the speed of light is constant for all inertial frames of reference. So meaning no matter what as long as you're in an inertial frame of reference, the speed of light is always the same. Oh, that's supposed to be gray. There we go. Let's make that gray too. Okay. So what does this mean? This means that the speed of light is constant no matter where you're measuring from. So what this means is that back to our old scenario. So we're gonna kind of ignore here right now. Back to our old scenario though. Bella's moving with the speed v. We don't even we'll say again. What do we say? 20 meters per second. And you're at rest. So here's the speed of you. I won't even use Earth or whatever. I'll say b Bella, vu 0. Okay, and then Bella shoots out light beam or a bit of light, a little chunk of light here. Boom, out it goes. And it moves with the speed of light c. So it moves with the speed of light c. Well, that means Bella is going to see that she's going to measure the speed of light as being c. She's going to look at this and go, oh, that's moving at a speed c, the speed of light, 3 times 10 to the 8 meters per second. And then you would also look at it, even though you're going 0 miles an hour with respect to the Earth, and you would look at it and you would go, yep, that thing's moving at the speed of light c. Even though Bella was the one who threw it out. So Galilean relativity would say, oh, that's c plus 20 meters per second. No, Einstein says. The second that light leaves Bella's paw, this thing is moving with the speed c. And Einstein goes even further, saying, let's say that Bella's rival, Lily, or, well, Bella would consider her best friend, but that's beside the point. But Bella's rival, Lily, who's moving to the left at 20 meters per second, would look at that same beam of light. She would look at that same beam of light, and she would go, yeah, everybody, yep, that thing is moving at the speed of light c. No plus 20, no minus 20, no nothing. Everybody would agree that the light is moving at the speed of light c. So that's what Einstein's saying, is that a chunk of light, or light in general, everybody measures it as going c, the speed of light in a vacuum, 3 times 10 to the 8 meters per second. And then he said, okay, what are the consequences of this? Here we go. So, same situation again, but we're going to call you A now. You're A. Bella's B. B for Bella, but A because I couldn't come up with anything special. You're at rest with respect to the Earth. For simplicity's sake, we're just going to call you VA. Probably not going to use it anymore because you're just at rest right there. And then you have next to you what we're going to call a light clock. This is a light clock. Boop. And the way it works is that it sends out a little chunk of light. Boom, and it bounces off a mirror and then comes back and then reaches a detector. So here you've got light, kind of an emitter. It sends out light. So it's a source of light. And then here we've got a detector. It detects the light. And so the time between the source being emitted and then it being detected, we're going to call delta t. So delta ta is time between source and detect. In relativity, we call this events. We could call this event 1 and event 2. So in relativity, we call that events. And then your perspective of Bella's light clock. Bella also has a light clock that does exactly the same thing. It's got the same height or distance d. Bella's light clock goes up once, down once, and the time it takes Bella's light clock, so delta TB, from your perspective, so time between event 1 and event 2, which is Bella's source being emitted and then it being detected, is TB. We call it TB. And that again, from your perspective there. Okay. There we go. And we're going to take this. We might use it again, but I don't think we're going to need it again. But if we do, it'll just be down here. So I want to keep this as simple as I can. In fact, I'm even going to erase light clock here. Okay, because the thing is that Bella's moving this way. She's got a speed v. She's got a speed v. And we're going to say she's moving fairly close to the speed of light. I don't know, 0.9 the speed of light or 0.8, something like that. And so at some next moment, she might be here, right? So she could start here, and then is here, and then at some third point here. So boop, boop, boop. And then here we got boop, 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 boop. There we go. And then her light source, from your perspective, though, is going to bounce like this because her light source is moving with Bella. So it's going to go boop, 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 and hit the detector. So it's going to go up, bounce off the mirror, and then hit the detector like that. So okay, let's start off with let's get an equation for because here the time it takes. Here is delta TA. Let's see if we get an equation for delta TA. So we're going to start with our typical distance equals velocity divided by time. Well, the distance traveled, well, distance, let's say it's capital D, because it's going to be twice D, right? Because the time it takes, delta TA, so this is delta TA. It's going to be twice D because it goes up once and then down. So it goes up a distance D and then down a distance D. So the total distance is twice D. That's the time it's going to take TA. And that's going to move at the speed of light c. Again, Einstein's postulate here is that the speed of light is constant. So, okay, if it's a light beam, if it's a bit of light, then we're going to call it, it's moving at the speed c. And then I'm going to solve for t sub a. That's going to be t sub a equals 2d over c. And we're going to hold on to that, because we might need that. And well, you're going to need that because you're doing the derivation here. I'm just setting you up. Okay, so next up we got here. What's going on here? Well, let's see. Let's start here. Let's say that Bella's moving along here, and we're going to stop here. So let's see. What's the amount of time it takes? So we're going to use the same equation here. The distance is equal to, we'll say the distance is called delta x, is equal to the speed multiplied by the time. Well, what's the time it takes to go from here to here? Well, that would be half of Bella's time, because Bella's time is going to be the time it takes that bit of light to go up here and back down. That's the total time. This is just half of Bella's time. So this is going to be 1/2 delta t. So well, let's throw it over here. 1/2 delta TB. And then the speed at which she's moving, well, we're calling it v. So her speed is v. Yeah, that's fine. The speed is v, and then that's delta x. So I think it's all we need. So we'll just throw it all over here. Delta x equals 1/2 v delta t b. All right. So there's that. We're going to use that as well. You're going to need that. The distance here is d. So let's throw it over here. And it's going to give you a little bit of a bit more of a hint. Okay, what about the time it takes to go from here to here? Well, that's also half of TB, right? That's half of TB. So let's throw it over here for right now. So again, the distance traveled. So say this is, again, I'll call it capital D. So capital D here is going to be the speed. The speed she's moving is c, and then the time it takes is TB. Oh, not TB. It's half TB. Because again, we're going from here to here. That's going to be half TB. So, so yes, that distance is half TB. So we'll call this 1/2 c delta TB. Okay. So with all that, and then we're going to use this too. So with all that, and you might want to use this as well. So hopefully you can see something. This is my hint to you, right there. Because it's kind of amazing. It's kind of amazing what you can do with Einstein. Okay, so what am I trying to do here? Okay, so here's the goal. Here's the goal. Using these equations or relationships, you're going to have to do some algebra and some trigonometry and things like that. But again, nothing too fancy. No derivatives here or anything like that. And you're going to get this expression. I want you to get this expression that delta TB is equal to delta TA divided by the square root of 1 minus v squared divided by c squared. See if you can do it. See if you can get there. Starting with those equations that I've highlighted, try and get what I've just put in this box here. Get to this. That the change in time of B is equal to the change in time of A divided by the square root of 1 minus V squared over C squared. So see if you can do that. Put it in the discussion, and I look forward to seeing what you get. All right. Good luck. Bye.